Imagine a movie that doesn't just, sweep you away on this breathtaking journey across the galaxy, but one that actually pushes the boundaries of scientific visualization so far that it leads to real, peer-reviewed scientific papers.
Yeah, actual new insights into the universe. It's kind of amazing when you think about it.
Exactly. Today, we're taking a deep dive into Christopher Nolan's epic film, Interstellar.
And you're right, this isn't just going to be another film review. Definitely not.
No way.
This is an exploration of the truly cutting-edge science woven into its very fabric. We're going to be unpacking the true-to-life physics that absolutely amazed audiences and scientists.
Right, the stuff they got spot on.
Exactly. Then we'll pivot to the, let's say, creative liberties taken for storytelling, because, it's still Hollywood.
Of course. Gotta serve the story.
Gotta serve the story. And finally, we'll venture into the really speculative theories that Interstellar so boldly brought to the big screen. Stuff that sparked conversations we're, frankly, still having today.
That's right. And for this deep dive, we've really tried to go directly to the source. We've sifted through insights from the filmmakers themselves,
Nolan, Thorne.
the brilliant theoretical physicists who consulted on the movie, like Kip Thorne. We looked at academic journals that actually published their findings.
Which is pretty wild in itself.
It really is. And even, popular science discussions from around the globe. Our goal here is to give you a shortcut to understanding what truly makes Interstellar such a landmark.
Yeah, not just in science fiction, but like you said, in scientific visualization and even public engagement with science.
Right. We're here to navigate that complex scientific landscape, highlight those aha moments, and carefully separate the undeniable fact from the, truly fascinating fiction.
So get ready to look up at the stars, not just down at the dirt, because what we're about to explore is genuinely, it's out of this world.
Okay, let's unpack this. Our journey begins with what truly set Interstellar apart from so many other science fiction films. Christopher Nolan's really unwavering commitment to scientific authenticity.
And this commitment was so profound, it led to this unparalleled collaboration with one of the most brilliant minds in theoretical physics, Kip Thorne.
Yeah, and it's so important to understand just how significant Thorne's involvement actually was. He wasn't just, a consultant brought in for a few quick chats.
Right, not just a name on the credits.
Not at all. Kip Thorne is a world-renowned theoretical physicist, an absolute titan in the fields of black holes, wormholes, gravitational waves, concepts that are, totally central to Interstellar.
The core of the movie, really.
Absolutely. He served as both an executive producer and the lead science consultant. His job was basically to ensure scientific rigor every step of the way. He was like the scientific conscience of the whole production.
Wow.
Yeah, so this wasn't a case of science being an afterthought or just, tacked on for a bit of credibility.
Like window dressing.
Exactly. It was fundamentally built into the very DNA of the film's production, right, from the earliest conceptual stages. So it wasn't just about making sure the dialogue sounded smart or, validating existing theories.
I know.
Their collaboration was so deep that it actually generated new scientific insights, new discoveries.
Yeah, think about that for a second. A Hollywood blockbuster, not just using science, but actually generating new peer-reviewed scientific papers.
It's mind-blowing. It sort of redefines the whole relationship between art and science, doesn't it?
It really does. It shows how the ambition of storytelling can, in turn, become this kind of crucible for genuine discovery.
So what did that actually mean for the film production day-to-day? For the effects team, for instance?
Well, it meant that Double Negative, the visual effects company, wasn't just, creating pretty pictures.
Okay.
They were effectively conducting a visual scientific experiment. They were pushing their computational boundaries to truly simulate these extreme astrophysical phenomena with really unprecedented detail.
So the movie itself was like a giant science experiment.
Pretty much.
Yeah.
A massive multi-million-dollar science experiment driving computational advancements that, even academia hadn't quite reached yet in certain areas. This commitment to hard science, as they called it, was totally central to Nolan's vision. It really set Interstellar in a league of its own compared to a lot of previous Hollywood sci-fi, which, let's be honest, often sacrifices accuracy for spectacle.
And speaking of unprecedented detail and spectacle, Gargantua, the film's supermassive black hole.
Ah, yes, Gargantua.
Its depiction was truly a triumph of accuracy, wasn't it? A testament to those massive scientific and computational efforts we just mentioned.
Absolutely.
I mean, it's one thing to have a theoretical physicist on board, but it's another for their actual calculations to define the visual effects.
Yeah.
What were the hurdles there? Did Nolan just say, go for it?
Well, it's kind of a classic Hollywood story, but with a science twist.
Mm.
Nolan himself initially was actually worried.
Oh, really?
Yeah, he worried that Thorne's scientifically accurate calculations for the black hole wouldn't look cool enough for the big screen.
Huh. You'd think the real thing would be the coolest.
You would, but he was concerned it might be too abstract, maybe too alien. Not visually dramatic enough for audiences used to, black holes just being cosmic drain pipes or something.
Right, the usual sci-fi tropes.
Exactly. But Thorne, with his deep conviction in frankly, the elegance of physics, persuaded him to go for it. Thorne insisted on working directly with the visual effects team. Double negative.
So he was embedded with them?
Pretty much.
Yeah.
To implement his complex equations for how the black hole's immense gravity would affect light, how light from its surroundings would be bent and distorted. This meant the VFX artists weren't just drawing, they were effectively solving Einstein's field equations.
Wow. So Thorne provided the mathematical blueprints, the really complex relativistic equations describing space-time around a spinning black hole.
Yep, the math.
And Double Negative, the VFX studio, brought the just immense computing power and the innovative software to visualize it.
That's the combo.
And the result, just this incredibly realistic rendering of a black hole, unlike anything that had ever been seen in mainstream cinema before.
Exactly. This wasn't just a guess or an artist's impression. It was a rigorous physics-based simulation.
And what's really fascinating, almost unbelievable, is the validation after the film.
Oh, this is the best part. 5 years later, right? 2019. The Event Horizon Telescope captured the first ever image of a real black hole, M87 star, way out in a distant galaxy.
I remember seeing that image. It was everywhere.
And when that image was released, to the astonishment of so many people, it bore this striking resemblance to Interstellar's Gargantua.
It really did, that glowing ring of light around a dark shadow.
Exactly what the film had rendered years earlier. Apparently, Christopher Nolan himself, when he saw the photo in the New York Times, he immediately called Kip Thorne. Reportedly said something like, well, I guess you were right. Very glad to see that you were right, and our black hole holds up.
That must have been an incredible I told you so moment, but in the best way.
Oh, absolutely. A total vindication of their shared commitment to getting the science right.
It really cemented the film's depiction, didn't it? It's kind of become the standard way of looking at it now for a lot of people.
For sure. Its influence isn't just in film. It's shaped how the public visualizes these cosmic giants. It was like a preview of actual scientific observations.
And it went even further than just public visualization, right? Didn't it lead to actual scientific papers?
It did. The collaboration between Thorne and Paul Franklin, the visual effects supervisor at Double Negative, actually led to them jointly publishing a couple different scientific papers.
Seriously, published papers from a movie's VFX work?
Seriously. And these weren't just, vanity projects. They were peer-reviewed articles in proper physics journals, like Classical and Quantum Gravity. They detailed the new rendering methods, the novel algorithms they used to trace light rays through that extreme space-time curvature.
So DNEG basically became a temporary astrophysics research lab.
In a way, yeah. They were exploring new computational techniques and insights into gravitational lensing that came directly out of the filmmaking process. It's such a rare example of cinematic ambition directly contributing to scientific literature.
That iconic glowing ring around Gargantua in the movie, you probably remember it vividly.
Oh yeah, unforgettable.
That's not just artistic license, that's the accretion disk, the swirling disk of superheated gas and dust feeding the black hole.
Emitting intense light, X-rays.
Exactly. But what makes it look so alien and beautiful in the film is that the disk itself is warped by gravitational lensing.
Right, it's not just a flat ring like Saturn's.
No. The black hole's immense gravity bends the light from the disk, creating these two images, one looping over the black hole and the other under it. This extraordinary halo, as Thorne called it, that was a key discovery for the VFX team. They found that the warping space around the black hole also warps the accretion disk itself into this almost impossible-looking shape, like a shining cosmic pretzel, sort of.
Yeah, it's a fantastic visual. And it's not just movie magic, like you said. It's a powerful example of how artistic ambition, when it's driven by a commitment to scientific principles, can actually propel scientific understanding forward.
It gave us a tangible preview, didn't it? A glimpse of what these real cosmic phenomena might look like years before we saw M87.
Exactly. Making the abstract theoretical real, making it something you can see, comprehend, and even connect with emotionally.
Okay, moving from the visual spectacle of Gargantua to the very fabric of time itself, Interstellar also portrayed gravitational time dilation really accurately, didn't it?
Oh, absolutely. A direct consequence of Einstein's general theory of relativity.
And this is where the emotional punch of the movie really lands for a lot of people. The just heartbreaking consequences of relativity made painfully clear.
Yeah, it's brutal. The core idea is simple enough. Time passes more slowly in stronger gravitational fields.
The closer you are to something really massive.
The slower time ticks for you, relative to someone further away, in weaker gravity. The film illustrates this so vividly, especially with the characters experiencing time differently depending on how close they are to Gargantua.
And the most dramatic, just gut-wrenching example is Miller's planet.
Well, Miller's planet, orbiting incredibly close to Gargantua. There, one single hour spent on its surface
Just 1 hour.
equals 7 years back on Earth, or even back on the Endurance orbiting further out. Imagine that weight. Every minute down there costs years of your children's lives.
That scene, it just hits so hard when you realize the cost. And Nolan apparently insisted that this extreme time dilation was non-negotiable for the story.
Crucial for the emotional arc, yeah. And Kip Thorne, digging into Einstein's relativistic equations, discovered that this specific magnitude of time dilation, that staggering difference, was only mathematically possible under very specific conditions.
Which were?
Miller's planet had to be extremely close to Gargantua, like skimming the edge, and Gargantua itself had to be spinning obscenely fast.
Obscenely fast.
Almost at the theoretical maximum spin speed for a black hole. Physicists use this ratio, A over m, AM, to describe spin. A is angular momentum, m is mass. A value near 1 is the max. Gargantua needed an AM of about 0.999.
Wow, right on the edge of possibility.
Right on the edge. Any faster, and the event horizon might not even exist in the same way.
So this isn't just some convenient plot device they made up.
Not at all. It's a cornerstone of general relativity. It's a proven aspect of our universe, though obviously we don't experience it to that extreme degree in our daily lives.
Thank goodness.
Yeah. But the film's depiction makes what is an abstract concept for most of us powerfully real and emotionally resonant. It highlights the profound, sometimes terrifying implications of living in a universe governed by these laws.
It forces you to feel the weight of time, or the lack of it.
Yeah, in different parts of the cosmos, especially when our human lives are so finite.
So if the black hole was pushing the limits of our understanding of time, what about space? How did the film tackle interstellar shortcuts? Wormholes.
Ah, the wormhole. Interstellar's portrayal here also aligned remarkably well with current scientific understanding, at least theoretically. It served as a scientifically grounded plot device to make interstellar travel even possible in the story.
So, wormholes. The official name is Einstein-Rosen bridges, right?
That's right. They're hypothetical shortcuts through space-time. Theoretically, they could allow rapid travel across vast cosmic distances, connecting two distant points like a tunnel through the fabric of space-time.
And the film really broke new ground visually, didn't it? How they showed it.
Totally. Unlike previous Hollywood movies that often showed wormholes as just like a swirling void or a psychedelic tunnel.
Yeah, the usual stuff.
Interstellar depicted it as a sphere, like a crystal ball hanging in space, and inside this sphere you could see this distorted image of the galaxy on the other side.
Oh, it was so cool.
It was. And that visual was meticulously crafted with direct input from Kip Thorne. It was apparently the first Hollywood movie to depict correctly a wormhole, as it would be seen by a nearby human.
So not just a tunnel entrance, but the whole sphere.
Exactly. You see the sphere itself, and because it's this massive gravitational object, theoretically, you'd see light from the other side bent around it. You'd even see its own gravitational lens, creating an Einstein ring on its outside that little circle of light.
A telltale sign of its gravity.
Precisely.
And the placement near Saturn. Was that just convenient, or?
Well, it was a creative choice,
Yeah.
but still scientifically grounded. Placing it within our solar system, near Saturn, made it relatively accessible for the Endurance mission. It demonstrated how these hypothetical structures could theoretically connect distant parts of the universe right from our own backyard, so to speak.
Sets the stage perfectly.
It does. But here's where it gets really interesting and maybe a bit paradoxical.
Okay.
The very existence of that wormhole near Saturn at the start of the film implies something fascinating we need to circle back to later.
Which is?
The question of who placed it there and how. That opens up a whole can of worms, pardon the pun, about causality itself.
Oh, right. We'll definitely get back to that paradox. But first, achieving these visuals gargantua, the wormhole required some serious tech, right?
Oh, absolutely. To get those stunning and scientifically accurate visuals, the production company, Double Negative or DNEG, they developed entirely custom code. They called it DNGR.
DNGR.
Double Negative Gravitational Renderer. This wasn't off-the-shelf software. It was built from the ground up, specifically for Interstellar, a massive undertaking.
And what was DNGR designed to do, exactly?
It was specifically designed to solve the incredibly complex equations for how light beams, or ray bundles as they called them, propagate through the curved space-time of a spinning black hole.
A curved black hole, right, not just a simple non-spinning one.
Exactly, a spinning curved black hole whose space-time is much more complicated than a non-spinning Schwarzschild one. The goal for DNGR was to render IMAX quality, rapidly changing images that were both scientifically precise and visually smooth. No flickering, no weird artifacts.
And it was a computational beast.
Oh, completely. Each single frame of the black hole sequence took approximately 100 hours to render.
100 hours for one frame.
Yep, so think about that. Every second of footage, which is usually 24 frames.
That's like 2,400 hours.
Roughly 100 days of computational time on DNG's render farm for every second of the black hole footage.
Wow. How big was this render farm?
It was huge. Apparently comprised something like 1633 Dell Blade servers, all networked together, running Linux, just crunching numbers constantly.
So what were those discussions like in the production office? 100 days for a single second of film. Was Kip Thorne just saying, nope, gotta be accurate, even if it melts the servers?
Oh, you can imagine the resource allocation meetings must have been intense. But yeah, Thorne's conviction in the physics clearly won out, alongside Nolan's vision. And the code itself used these ray bundle techniques.
Ray bundles, how's that different from how physicists usually do it?
Well, physicists often model things by tracing individual light rays, one by one. DNGR worked more like firing a whole spray or bundle of light beams through the curved spacetime.
Okay, like a shotgun blast of light instead of a single bullet?
Kind of, yeah. And this approach was crucial because it allowed for that IMAX quality smoothness without flickering.
Yeah.
It gave that incredibly fluid, almost real-time look to things like gravitational lensing, especially with a moving camera, which tracing individual rays struggles with for cinema.
And the technical demands didn't stop there, did they? It had to handle relativistic effects, too.
Absolutely. DNGR needed to incorporate really specialized effects, like relativistic aberration, how the direction of light appears to change when you're moving really fast. Doppler shifts, how light changes color and brightness depending on whether the source is moving towards you or away.
Yeah.
Like the red shift and blue shift.
Right.
And gravitational red shifts where light loses energy and gets redder as it climbs out of a strong gravity well. This was super critical because the camera in the film would sometimes be moving at a significant fraction of the speed of light.
Yeah.
That dramatically changes how everything looks.
So how did they manage all that complexity?
They developed novel filtering methods. Spatial filtering to smooth things out between the different light beams, ensuring seamless visuals. And temporal filtering to simulate motion blur realistically.
Motion blur.
Like creating those streaks of light for stars that are moving rapidly across the screen, especially near what they call critical curves, where light rays can orbit the black hole multiple times before escaping to the camera. It wasn't just about making it look pretty, it was about accurately simulating the physics of light in these extreme conditions.
So again, this wasn't just film magic. The work on Interstellar literally created a new simulation code capable of exploring black hole lensing with, well, unprecedented image smoothness and dynamics.
Exactly. It pushed the boundaries of what computational astrophysics could visualize at the time.
And I read something interesting about how it handled stars compared to other methods.
Yeah, that's a good point. Unlike some other gravitational lensing codes that might use, say, a 2D picture of a galaxy as the background source, which can lead to unrealistic stretching or squashing of the stars within that image when it gets warped.
Right, they'd look distorted.
DNGR's light beam technique treated stars as individual points of light. By tracing their ray bundles through the warped spacetime, it maintained their natural, crisp appearance even under extreme lensing. They didn't get unnaturally smeared out.
That's a subtle but really important detail for realism.
It is. It really highlights how the film pushed the boundaries of the visualization tools themselves, creating something pretty revolutionary for both cinema and potentially science.
Okay, so we've established the incredible commitment to accuracy, but as scientifically rigorous as Interstellar aimed to be, it is still a Hollywood film.
Right. and sometimes science has to meet storytelling halfway.
Which means compromises,
Yeah.
aesthetic adjustments, creative liberties taken for visual clarity or maybe dramatic impact.
Exactly, it's a pragmatic balance. While Gargantua was largely accurate, certain scientific elements were intentionally altered for, visual clarity and mass audience appeal.
Like what, for instance?
Okay, take the black hole's spin again.
Yeah.
For that crazy time dilation on Miller's planet to work.
The 1 hour equals 7 years thing.
Right. Gargantua needed that obscenely fast spin we talked about, the AM near .999.
Okay.
But Christopher Nolan and Paul Franklin, the VFX supervisor, they decided that showing this ultra-fast spin accurately would be too confusing for a mass audience.
Why confusing?
Because a scientifically accurate rendering of such a fast-spinning black hole would make the accretion disk look exceedingly lopsided. One side would be way brighter and more distorted than the other, and the black hole's shadow itself wouldn't be circular. It'd be heavily D-shaped and maybe barely discernible amidst the bright disk.
Ah, so less iconic looking.
Much less.
Yeah.
So, purely for visual purposes, they deliberately slowed the spin in the final visuals down to an AM of about 0.6. This was a conscious choice to make it look more visually balanced, more symmetrical, more, aesthetically appealing. It let the audience clearly see that iconic black hole silhouette.
Okay, that makes sense from a filmmaking perspective. What else?
Similarly, those color and brightness shifts the Doppler and gravitational shifts.
Right, the blue side and the red side.
Scientifically, the side of the disk moving toward the camera should appear intensely blue and very bright. The side moving away should look dim and very red. We see effects like this in astrophysical jets.
Okay.
But Nolan and Franklin chose to omit the Doppler shifts in the movie. Again, to maintain a more balanced visual, something particularly appealing that wouldn't distract from the central image of the black hole itself. They prioritized that visual harmony over absolute fidelity to every single physical effect.
So if they hadn't made those specific changes, slowing the spin visually, removing the Doppler shift, Gargantua would have looked extremely distorted, asymmetrical.
Yeah, probably quite jarring and maybe confusing rather than awe-inspiring for a lot of viewers.
It's that pragmatic decision again, isn't it? Balancing the realism with the need for a compelling cinematic experience that doesn't just overwhelm the audience with too much raw scientific complexity.
Exactly. It highlights that constant tension in good science fiction. How much accuracy can you maintain without potentially alienating a general audience or sacrificing the sheer cinematic impact? It's a delicate dance.
A dance between education and entertainment.
Precisely. Sometimes a small compromise on the strict physics can lead to a much larger, more resonant storytelling experience for more people.
Okay, so beyond those deliberate aesthetic tweaks, the film also included some elements that were maybe more scientifically debatable or even arguably inaccurate, again, maybe for plot or drama.
Yeah, this is where we get into some of the common misconceptions that perhaps the movie, despite its overall scientific cred, might have even reinforced a little.
Or just places where they bent the rules for the sake of the plot.
Right. One noticeable example is Gargantua's apparent field of view in the sky.
How big it looked.
Exactly. In the movie, when the Endurance crew is at that distance of about 5 Gargantua radii, which, remember, is roughly the Sun to Jupiter distance.
Okay, pretty far out still.
Gargantua appears to take up about 2.5 degrees in the sky. Now, for perspective, that's about 5 times the size of our full moon. Feels huge in the movie, right?
Absolutely massive. It fills the screen.
But in reality, because of its true immense size and the extreme gravitational lensing happening that close, it should have taken up a staggering 50 degrees of the sky.
50 degrees? That's huge. Way bigger.
Way, way bigger, almost filling their entire view screen. It would have been almost incomprehensible, probably visually overwhelming. So that was a significant simplification for the screen.
Okay, that's a big difference. What else?
Well, back to Gargantua's spin again. Remember how the time dilation required it to be spinning super fast?
Yeah, the physics demanded it.
But visually in the movie, the black hole looks like a non-spinning Schwarzschild black hole, the kind with a perfectly circular shadow.
Instead of the D shape it should have had.
Exactly. Yeah. A spinning Kerr black hole, like Gargantua must be for the time dilation to work, would have that distinct D-shaped asymmetrical shadow. Again, Nolan chose to simplify the visual for the audience, favoring the more iconic, symmetrical image we associate with black holes.
Okay. And then there was that line from Amelia Brand about black holes sucking things in.
Ah, yes. That actually touches on a very common misconception. She says something like, when you're orbiting a black hole, not enough can happen. It sucks in asteroids and comets.
Which sounds plausible, right? They're cosmic vacuum cleaners.
Well, that's the misconception. In reality, it's insanely rare for objects to actually fall into a black hole once they're in a stable orbit.
Ooh.
Most objects with enough angular momentum, enough sideways motion, will just orbit indefinitely, just like Earth orbits the sun and doesn't fall in. Black holes aren't indiscriminate vacuum cleaners. You basically have to be on a direct collision course or lose almost all your orbital energy and momentum to fall in.
So Brand was wrong.
Technically, yes. But interestingly, Nolan knew this was inaccurate.
He did. Why include it then?
Apparently, he chose to include it anyway, maybe as a way to show that nobody's perfect, not even a brilliant scientist like Brand. It kind of humanizes the characters and their understanding, even if it's not strictly factual physics.
Okay. Interesting character choice. What about the neutron star swing shot? That looked dangerous.
Oh, that was really stretching things. Cooper tries to use a neutron star's gravity to break the Ranger for that tricky docking maneuver.
Yeah.
Realistically, given the likely speeds involved and the extreme density and gravity of a neutron star, such a close pass would expose the crew and the ship to insane tidal gravity forces.
Tidal forces. Like the moon causes tides on Earth, but way stronger.
Way, way stronger. Strong enough to tear both the spaceship and the crew apart. It's a process called spaghettification.
Spaghettification. Seriously.
The gravity difference between, say, your head and your feet would be so immense it would stretch you out like spaghetti. Not pleasant.
It's definitely not. So how could they have survived that?
They couldn't have. Not with a neutron star. For a slingshot like that to work without being shredded, they'd need a gravitational source with maybe similar overall gravity, but spread over a much larger area, like a, say, 10-kilometer wide intermediate mass black hole.
Why would that be different?
Because the gradient of gravity, how quickly it changes over distance, would be gentler. With a compact neutron star, the gravity changes incredibly rapidly across the length of a ship. With a larger black hole, the change is more gradual, so the tidal forces are less extreme at a survivable distance.
Okay, that makes sense. Any other little things?
There were a couple of minor ones flagged. One physicist noted a scene where the ship seems to bounce off a solid frozen cloud. I wasn't convinced any real material could freeze like that in space to form such a solid obstacle. He kind of shrugged it off as cinematic license.
Okay.
And also the way the shuttlecraft, the Ranger, takes off from planets like an airplane and reaching into interplanetary space.
Yeah, they just sort of lift off.
Realistically, getting off a planet with significant gravity requires a very substantial rocket with current tech, massive booster stages, huge fuel tanks, not just a sleek shuttle effortlessly lifting off.
Right, like the Saturn V versus the Space Shuttle Orbiter.
Exactly. So these examples, they really show that Interstellar's primary goal wasn't just scientific accuracy above all else. It was also about creating a compelling narrative.
And sometimes that narrative needed things to happen that bent the rules a bit.
Precisely. It's the art of compromise in sci-fi filmmaking. The overall plausibility and emotional impact sometimes have to outweigh absolute scientific fidelity in every single tiny detail.
Okay, let's push beyond the more tangible science now and into the really mind-bending stuff. The speculative physics and philosophical depths that Interstellar dares to explore.
Yeah, this is where the movie really gets you thinking long after the credits roll. It delves into concepts right at the frontier of theoretical physics.
Starting with the Tesseract and the whole idea of a fifth dimension.
Right. The enigmatic fifth dimension. The film links it directly to themes of time, gravity, and even causality. It conceptualizes this fifth dimension as somehow encompassing every possible timeline of a third-dimensional universe.
Okay, wait. So our normal 3 spatial dimensions plus time makes 4.
Right, that's our familiar space-time.
And this fifth dimension contains all possible versions of that 4D space-time.
That's the idea presented. Imagine it not as a single line of time, but as a higher space, where all potential timelines, past, present, future, maybe even alternate histories, coexist or are accessible.
Whoa.
This is how the advanced beings in the film, who are implicitly future, evolved humans, are able to perceive time differently. They see hindsight and foresight as 20/20. They're infinitely wise, in a sense.
Because they can see all outcomes.
Exactly. They can see every failure timeline and every successful timeline, which allows them to intervene to set up Cooper for success by guiding his actions through gravitational anomalies from within this higher dimension, the Tesseract.
And crucially, the film suggests only gravity can cross these dimensions, right?
That's a key point. These theoretical models often suggest that only gravitational fields can propagate freely into this higher dimensional bulk universe, while other forces like electromagnetism, light, radio waves, etc., are confined to our four-dimensional brain.
Our universe is a brain, like a membrane.
Yeah, think of our 4D universe as just a slice or a membrane existing within a larger, higher dimensional space called the bulk. And if only gravity leaks into the bulk.
Then communication from the bulk to our past could only happen using gravity.
Precisely. That explains why Cooper, inside the Tesseract, could only interact with young Murph's inner bedroom using simple codes delivered through gravitational effects, pushing books, manipulating dust, making the watch hand twitch. He couldn't just yell or shine a light through.
Is this just movie magic, or is there any basis for this in real physics?
Well, it's highly speculative, but it is rooted in serious attempts by physicists to understand things like quantum gravity and the hierarchy problem, why gravity is so much weaker than other forces. Models like the Randall-Sundrum models, for example, explicitly propose our 4D universe as a brain within a 5D bulk. And in these models, gravity can propagate into the bulk, which could explain its apparent weakness in our dimensions. So the film is tapping into some quite sophisticated, albeit theoretical, physics concepts here.
So while it's way out there, exploring these ideas really encourages deep thought, doesn't it? About the nature of reality, time, our place in the cosmos.
Absolutely. It challenges our everyday linear perception of time and space. It's genuinely mind-bending stuff.
And building on that, Interstellar really dives headfirst into a profound logical paradox involving the wormhole itself.
Yes, the causality loop.
Right. How could future humans place the wormhole near Saturn if they needed that wormhole to survive and become those future humans in the first place?
It's the classic bootstrap paradox, or a causal loop. Seems like a chicken and egg problem that breaks our normal sense of linear cause and effect. A causes B, B causes C.
But here, it seems like the effect, future humans building the wormhole, is somehow the cause of the cause. Humanity surviving using the wormhole.
Exactly. But the film's answer, and Kip Thorne's likely input here, is key lies in the weirdness of general relativity and the idea of nonlinear causality.
Yeah.
In our ordinary experience, cause always precedes effect. But in general relativity, where space-time can be severely warped and even folded by massive objects or exotic matter, causality is not so simple.
Space-time can fold back on itself.
Theoretically, yes. It could allow for what physicists call closed time-like curves, paths through space-time where you could march toward the future, but then eventually end up somewhere in what we would have originally called the past. Time travel, essentially, though not necessarily in a controllable way.
So the paradox isn't necessarily a paradox in relativity.
The key concept here is self-consistent history. It's often associated with the Novikov self-consistency principle. The idea is that if time travel loops exist, they must be internally consistent. You can't go back and say, kill your grandfather before you were born, because that would create a true paradox. The laws of physics might conspire to prevent it.
Okay. So how does that apply to the wormhole?
The film's narrative implies a self-consistent loop. Humans survived long enough to develop wormhole technology because the wormhole was already there to save them from the blight.
And the wormhole was there.
Because those future humans survived, thanks to the wormhole being there, and eventually built it and placed it in the past. It's a closed loop.
So either event can be seen as the cause of the other?
Exactly. There isn't necessarily a contradiction from a relativistic standpoint as long as the entire sequence of events is internally consistent. The loop just is.
That feels very circular, but maybe that's the point.
I think it is. And this apparent paradox was almost certainly quite intentional, given Kip Thorne's deep expertise in these specific causality issues. He's written extensively about wormholes, time travel, and these consistency problems. It's designed to make you grapple with time in a fundamentally different way.
It ties beautifully into that recurring theme, doesn't it? Mankind was born on Earth, but we were never meant to die here.
Yeah, echoing Dylan Thomas's poem, do not go gentle into that good night. It's not just about physically leaving Earth. Maybe it's also about transcending our limited linear understanding of existence, striving to learn more, reach for the stars, thrive and grow, even if our journey through space-time is far more complex than we imagine.
The film also, maybe more subtly, touches on the sheer difficulty and feasibility of long-term human space missions. That's a very real challenge we face as we look towards Mars and beyond.
Absolutely. The character's physical and mental endurance is constantly tested, and that reflects real-world concerns. Long-term space travel presents numerous, very serious physical hazards.
Like what? We hear about bone density loss.
That's a big one, yes. Microgravity exposure leads to significant cardiovascular changes, to fluid shifts, the heart potentially weakening. Muscle atrophy is another major issue.
So astronauts have to exercise constantly.
Rigorously. Often 2 hours a day on special treadmills and resistance machines, just to maintain muscle and bone mass. Then there are visual impairments, something called SANS, spaceflight-associated neuroocular syndrome, affecting eyesight. And various neurological effects on the brain are still being studied.
And that's just microgravity. What about radiation?
That's arguably the biggest long-term hurdle for deep space travel. Outside Earth's protective magnetic field, astronauts are exposed to much higher levels of galactic cosmic rays and solar particle events. This significantly increases lifetime cancer risk and can potentially damage various organ systems, including the brain and central nervous system. We don't have perfect shielding solutions yet.
And beyond the physical toll, there's the psychological side.
Huge challenge. Isolation and confinement. Being cooped up in a small space, millions of miles from home, potentially for years.
Cut off from Earth, from loved ones.
Facing constant danger, monotony. It puts immense stress on mental health. Maintaining crew cohesion and psychological well-being is critical.
How do space agencies prepare for that?
Astronauts go through rigorous psychological screening and training. Mission control provides support. Countermeasures involve careful scheduling, providing meaningful work, communication links, recreation, but it's tough.
The film hints at advanced life support, but it feels like future tech will need even more.
Definitely. Things like advanced closed-loop systems for recycling air and water become essential. And looking further ahead, emerging technologies like AI could play a massive role.
AI, how?
AI-powered predictive models could monitor astronaut health data in real time, flagging potential issues early. AI diagnostic tools could help analyze medical scans or symptoms. Telemedicine systems, maybe AI-assisted, could allow for complex remote consultations with Earth-based specialists. It could really help manage health risks and psychological well-being on those super long missions.
So when we watch Cooper and Brand struggling, it's not just drama. Understanding these real challenges puts their journeys in Interstellar into a sobering light.
Sobering yet inspiring, too. Their sacrifices and struggles are grounded in very real potential hardships that future explorers will face. It makes their determination feel even more profound.
Okay, and finally, let's talk about maybe the most philosophical and certainly the most debated aspect of Interstellar. Love. Love is a fifth force, something that transcends time and space. This is where the movie really veers into the poetic, but it frames it almost scientifically.
It does. It's famously introduced through Amelia Brand's monologue, right? Maybe we spent too long trying to figure all this out with theory. Love is the one thing that transcends time and space.
She doesn't just say it's important, she posits it as potentially observable, powerful, maybe even an artifact of higher dimensions that we can't consciously perceive.
Yeah, it's presented almost like a scientific hypothesis about this deeply intangible human emotion.
And narratively, this irrational love, especially Cooper's desperate love for his daughter, Murph becomes this incredibly powerful driver.
Absolutely. It's what fuels him. It's what propels him through seemingly impossible feats, risking everything to dock with the wildly spinning Endurance, venturing into the singularity of Gargantua itself.
And then guiding his actions inside the Tesseract to save humanity through that connection with Murph.
Exactly. It's the emotional core that makes all the complex physics relatable. It gives the whole journey a deeply human purpose. Without that love, Cooper's motivations, his choices, they just wouldn't make nearly as much sense.
It definitely invites some profound philosophical questions, doesn't it? Is love somehow like gravity, this fundamental force pulling us together across vast distances, maybe even through time?
Could it be tied to the very fabric of existence? Some people even used if it connects metaphorically to things like the Higgs field, which gives particles mass, gives existence structure. Maybe love gives it meaning.
It suggests this almost cosmic connection between our most intimate human emotion and the grandest physical laws.
Now, it's important to temper this a bit. A theoretical physicist who consulted on the film reportedly noted that this is where sometimes Hollywood just can't help itself.
So, more poetic flourish than literal physics.
Pretty much. It's not a literal fifth force in the way physicists talk about forces. But that same physicist also emphasized how crucial it was to embed these complex physics concepts in a human story.
Why?
Because physics, ultimately, is about describing the structure of our experiences. And when those abstract structures are framed in human terms with relatable emotions like love, it helps us more fully come to terms with it. we connect with it better.
So while love isn't literally a fifth force, it acts as the film's profound emotional anchor. It lets us connect with the unimaginable scale of space and time through a very human lens.
Precisely. This is where the movie truly transcends the hard science, using it as a springboard for these deep human and existential questions about what drives us, what we value, and what impossible things we might do for those connections, even when logic screams otherwise.
Okay, as we start to wrap up our deep dive here, let's think about Interstellar's enduring impact and the debates it continues to spark. Despite those scientific liberties we discussed, its legacy seems pretty undeniable.
Oh, for sure. It's resonated hugely with scientists and, just dreamers alike. It's been widely praised by academics for its immense potential to inspire scientific curiosity, especially in younger people.
I remember reading about a physics journal actually recommending it.
That's right. A leading academic journal, the American Journal of Physics, published a paper arguing that Interstellar should be shown in school physics lessons.
Wow, in physics class?
Yeah, specifically because of its groundbreaking graphics portraying wormholes and black holes accurately. The journal's editor apparently called publishing the article a no-brainer, recognizing its sheer educational value in visualizing these incredibly complex phenomena derived from general relativity.
That's quite an endorsement from the academic world.
It really is. And Christopher Nolan himself said he hoped that by dramatizing science and making it something that could be entertaining for kids, we might inspire some of the astronauts of tomorrow.
And it feels like it might have worked, to some extent. Its commitment to grounding itself in theoretical physics, even the speculative stuff, definitely sparked genuine interest in conversations about the universe.
It showed that physics isn't just dry equations on a blackboard, it's the blueprint for these incredible, awe-inspiring realities out there.
And the science work behind the film didn't just produce visuals, right? It had real research outcomes.
Yeah, as we mentioned, it generated actual research opportunities. Kip Thorne published findings based on the black hole modeling work done with DNEG and the DNGR code.
Like what kind of findings?
For instance, they apparently discovered some previously unobserved subtleties in light-bending effects when simulating gravitational lensing around those rapidly spinning black holes, insights that emerged directly from the demands of the visual effects production.
That's amazing. Cinematic production directly contributing to new scientific literature.
It's rare and incredibly impressive.
However, the film wasn't universally praised on all fronts. It also faced some criticism, didn't it, regarding its underlying themes?
That's true, particularly themes of human expansion and what some critics perceived as elements of American colonialism, or maybe a problematic approach to environmental issues.
Right. It's important we acknowledge those viewpoints, too, as part of the whole discussion around the film.
Absolutely. The film's basic premise, remember, is that humanity deserves to go to the stars, that will suffocate if confined to Earth, especially with the blight and the dust storms.
Leading to this desperate mission to find new habitable worlds.
Exactly. And some critics pointed to what they saw as an American-centric presentation. NASA acting alone as humanity's saviors, mostly American actors, American flags popping up on the settled colonies.
Okay, I can see that interpretation.
Some went further, interpreting it as a dangerous fantasy of U.S. colonialism, drawing parallels to historical patterns of expansion and perhaps exploitation.
Were there other issues raised about the premise itself?
Yeah, some critics question the unquestioned assumptions. For instance, why did this civilization, which it's implied basically murdered its home planet through human-caused climate change or some kind of environmental mismanagement, why didn't they seem to focus on making fundamental changes in its approach to social construction and resource use on Earth?
Instead of just leaving.
Right. Is space colonization presented too easily as the solution, rather than fixing our problems here? It raises questions about whether we're just exporting our problems or truly finding a sustainable path.
That's a fair point to consider. What about the new planets themselves?
There was also the ecological angle. The film doesn't really grapple with whether human expansion might kill off the new planet's current residents, assuming any exist, or whether the undoubtedly fragile ecosystems on these potentially pristine worlds would be just irrevocably destroyed by earthly germs, invasive species, resource extraction.
The typical footprint of human arrival.
Pretty much. These are valid critical perspectives that highlight the really complex ethical and philosophical dimensions of humanity's future in space. They prompt viewers to consider the full implications of interstellar migration, beyond just the survival imperative.
But the film tries to counter that with the love theme, maybe.
Possibly. You could argue the film's focus on love as this transcendent force tries to shift the focus towards a more universal human drive for survival and connection, perhaps aiming to move beyond those potential colonialist undertones. It's definitely part of the complex conversation the film generated.
Well, we've taken quite a journey ourselves here through Interstellar's scientific landscape. From its remarkably accurate depiction of black holes later validated by actual observations,
Amazing.
to its creative, necessary alterations for storytelling, and its really bold exploration of speculative physics, like the fifth dimension and that mind-bending, nonlinear causality.
It really does strike an impressive balance, doesn't it? Grounding so much of its narrative in established physics principles, while still taking those calculated liberties to serve its powerful story, and just, wow, those awe-inspiring visuals.
It's such a profound reminder that science and imagination aren't mutually exclusive at all.
Not at all. In fact, they can feed each other in these incredible ways, pushing the boundaries of both artistic expression and scientific understanding.
So as we leave you to ponder all this, if, as the film suggests, love is the one thing that transcends time and space, and if maybe our ultimate purpose is to strive to learn more, to reach for the stars, what might your personal fifth dimension look like?
What unseen forces or connections might be guiding your own journey?
And what seemingly impossible feats might love compel you to achieve when you're faced with your own necessity to defy the impossible? Think about that.